We've covered quite a bit of material about Exergy balanced closed systems, open systems. We have to cover efficiencies. Another efficiency. We had efficiencies that were defined for the turbine, for the compressor, for the pump, for the heat exchanger. Actually not for the heat exchanger, but they were isentropic efficiencies. Now we're going to have exergetic efficiencies. Whenever you have an efficiency, think of trying to find the efficiency as a ratio that's going to be less than 100%, but the ratio is going to be what you want or desire over what it costs or what has to be provided. Okay, so let's take a look at a turbine. A turbine has an inlet fluid stream and an outlet fluid stream, and so the fluid stream goes through. Typically, the fluid is provided at high pressure, high temperature, a lot of thermal content to the fluid stream. You want to take some of that thermal energy of the fluid stream and convert it into shaft work or shaft power. So now, if you think about an exergetic balance around this device called a turbine, it's the flow exergy coming in compared to the flow exergy going out. So what do we want? We want a large power out the shaft. What does it cost? The mass flow rate times the difference between the inlet and the exit flow exergy. So that's our exergetic efficiency for a turbine. Numerically, it'll be very close to the isentropic efficiency for a turbine, but it won't be precisely the same. Okay. How about another device? How about talk about the exergetic, sometimes called the second law efficiency for a compressor or a pump. Now, the compressor or pump, you can work it out where you have the power going out of the compressor, but we know that the power is really into the compressor. Okay? So let me just do this. I'm going to abandon the sign convention, and I'm going to say W dots into that device, into the pump, into the compressor. And we go back, we say our exergetic efficiency for this pump or compressor is a ratio of something that we want or desire. What do we want for this pump or compressor divided by what it costs, what we have to provide. Well, what do we desire in this case? We really want to boost up the fluid flow exergy. We want this to be much greater than the inlet flow exergy. So what we want is a high increase in the exergy of the fluid stream. It came in at EF1, it goes out at EF2. All right, what did it cost? W dot. And again, I make that positive for my abandoning the traditional sign convention. Sometimes you'll see it where they go, oh, let's put a minus here. Well, that's because they stuck with the traditional sign convention. All right. How about an exergetic, also called second law efficiency, for a heat exchanger without mixing? So you think of a hot stream passing on one side. You have a metal plate separating it from a cold fluid passing on the other side. So the hot fluid on top, the cold fluid on bottom. They don't mix. Maybe it's copper tubes or some other metal that separates the two fluids. Okay. In this case, let's talk about the heat transfer. There's a heat transfer from the hot to the cold, true? Now, whenever you have a heat transfer, do you have exergy transfer with that heat? Yes, you do. A lot of times we'll draw it like this, E dot Q. So there's an exergy transfer from one fluid stream to another fluid stream in this heat exchanger. Okay, let's do this. So what we want is to define an exergetic efficiency for this. It's really a counterflow heat exchanger. Sometimes I'll add a subscript on that to help clarify. And it's a ratio of what we want to happen over what it costs or what drives it or makes it happen. Okay, so this one you have to think about for a little bit. What makes it really work? Well, it makes it work that the hot fluid's hotter than the cold. And so something's coming out of the hot stream. That's what's driving it. And something's going into the cold stream. So what it costs is out of the hot, and what you want is into the cold. Does that help? So when you turn this into what you want, that's into the cold stream. It's mass flow rate of the cold times EF4 minus EF3 divided by what came out of the hot, m dot hot times EF1 minus EF2. Now we have a different type of heat exchanger. It's a mixing or direct contact heat exchanger. We can also identify or describe an exergetic efficiency for this heat exchanger. Think about, I come in with the hot fluid here. I come in with the cold fluid here. What do I go out with? A lukewarm fluid. But the mass flow rate going out, there's only one outlet, m dot 3. Does it make sense that it's equal to m dot 1, what came in with the hot, plus what came in with the cold? Sure, that's a mass balance for that heat exchanger. So think about the hot fluid kind of going from hot to warm. Think of the cold fluid going from cold to warm. Okay? And in that mixing process, there's a heat exchange from the hot stream to the cold stream. It just so happens that the cold and the hot come out at the same temperature and they're warm together. So if that helps, then what we do is we say the exergetic efficiency for this direct contact heat exchanger would be what we wanted, well, the mass flow rate of the cold fluid times the increase in the exergy, EF3 minus EF2, divided by the mass flow rate of the hot fluid times its decrease in exergy, EF1 minus EF3. Does that make sense? Yeah. So you see that it's high goes to low, it's low goes to something higher for the flow exergy. One last exergetic, or also called second law efficiency, and it deals with heat engines. Okay, so I have a heat engine here. It's a system. Why do we put a box with a circle like that? What's that circle, going around like this? What does that indicate? It's a cycle. The system's operating in a cycle. As it's operating in a cycle, this heat engine takes in from a large thermal reservoir, that's a high temperature thermal reservoir, in this problem is 600 Kelvin, it takes in some heat, Q sub H. The goal of that heat engine is to convert as much of that Q sub H into useful work. But second law, Carnot efficiency, limitations on the conversion of heat into work, you know that you must have a lower temperature thermal reservoir which acts as a sink, and this one is at 300 Kelvin, and you dump off some part of that energy that was transferred in. Some of that heat, QH, that came into the heat engine has to be thrown away, QC, to the low temperature reservoir. All right? And so before we had an efficiency, it was called the thermal efficiency for this heat engine. What was it? Something I really want over something that I had to feed it or provide, or what costs. It's the ratio of W over QH. True? Right. Now what I want to do is I want to talk about exergy, and I still want to use that same illustration. Is there a flow of exergy with the heat transfer from the high temperature reservoir? Sure. Is there any exergy transfer with the work coming out, that shaft work coming out? Sure. And could there be some exergy transfer with the heat going to the low? There could be. What is our model for this it's 1 minus T naught divided by TH times QH, true? Okay, what is our model for the exergy transfer with the work? Is that equal to 100% of the work? Just work by itself, forget the 1, but I just put 1 in there because it's 100%, it's 1 to 1. And then this is 1 minus T naught over TC to the QC. So yeah, why is this one here equal to 0? It's because in this problem, TC and T0 are the same. They're 300 Kelvin, and so it's 0. And often what happens is when you throw heat out of a heat engine, you're not going to have another heat engine to make use of it. It's going to go to the environment, and so you just neglect it. It goes. There's no exergy transfer with that heat transfer. All right. So for this problem, let's go ahead and make a computation. All right, let me go back down here. For this problem, what was our work? It was 400 kilojoules. What was the QH coming in? 1,000 kilojoules. What is our thermal efficiency? 40%, isn't it? Now, anybody play with, sports? Maybe you had a football coach or whatever, and they're pepping you up right before the game, and they say, all right, team, go out there and go give it your full 40%. It doesn't sound good. There's no coach that ever said, go give it your full 40%, was excited to do that. It's 100 to 110%, right? You can't give 110, but it sounds like great. But anyway, now the exergetic efficiency, let's make some calculations and then compare it. So for this problem, you have 1 minus T naught over TH. That's 1 minus the 300 over the TH was 600. Okay. And then you have times the 1,000 kilojoules. Okay, can you do that one in your head? 500 kilojoules. Hey, kilojoules look like an energy, unit of energy. It's also the same unit for exergy. So 500 kilojoules of exergy come in with that 1,000 kilojoules of heat transfer. Now, how many kilojoules of exergy go out with the work? 400 kilojoules. So if you have an exergetic efficiency for a heat engine, it's what you want. We want the exergy transfer with the work over the exergy transfer with the heat coming in. In this case, I made that line a little too long. In this case, it's 400 kilojoules over 500 kilojoules. And the exergetic efficiency for the same heat engine, the same operating conditions, sounds a lot better. It's 80%. True? True. As a design engineer, you like to work where a goal is that you could max out at 100%. Okay? And where do you really max out? You max out at the Carnot efficiency. What is the Carnot efficiency for this heat engine, for these temperatures? 1 minus, T cold or TC over TH, so 300 over 600. What is the maximum efficiency? 50%. 50% is the theoretical limit on the thermal efficiency given the temperatures of the reservoirs. Okay? And then you see how you get the answer. Oh, well, we're only getting 40%. 40% compared to 50%. Hey, that's 80% of the way. Hopefully those numbers make sense. Make sense? Let's solve a problem. Let's solve a problem. Steam at 0.3 kilograms per second flows through a valve. It enters at a given pressure. So maybe we draw a valve like this, and we have the inlet condition 1 and the pressure 1 and the temperature 1 are given at 320 degrees C at 60 bar. And it exits at state 2, and the pressure at 2 is 20 bar. So there's a 40 bar pressure drop across the valve. Determine the rate of exergy destruction in the valve in units of kilowatts. What are they asking me to calculate? What symbol do I want to use? the rate of exergy destruction in kilowatts for part A. Let's solve for part A first. What I'm going to do is I have two strategies whenever I need to answer the question, what is the rate of exergy destruction? Either I can go with an exergy balance to calculate it, or I can calculate the rate of entropy production and multiply that by the dead state temperature T0, and I've got it. All right. Now, to do a rate of entropy production, guess what type of balance I do? An entropy balance. So you're going to do a balance. It's just whether or not you feel more comfortable doing an exergy balance or an entropy balance. So at this point, we'll do a show of hands. Who would like to go with an exergy balance? Who would like to go with an entropy balance? Okay, so it looks like entropy balance wins. Okay, we'll do it that way. So first thing is go ahead and get H1, S1. If you get H1, it's 2952.6 kilojoules per kilogram, and S1 is 6.1846 kilojoules per kilogram Kelvin, straight from the tables. Now, when I do I have to fix state 2 because I want to do an entropy balance around this valve. Okay. Is there any Q dot for that valve? Is there any W dot for that valve? So there's no heat transfer, no work transfer, steady flow through the valve. And what do we know from our energy balance? We know that H2 is equal to H1, so there is H2, 2952.6 kilojoules per kilogram. Just like these two independent intensive properties fix state 1, so I was able to look up other properties like S1 and H1. These two properties fix state 2, hence I can now theoretically look up, but it'll take me interpolation. I'll have to interpolate. But I can get the property S2. I'll have to interpolate in the superheated steam tables to do that. It's not a hard interpolation, but I get 6.6381 kilojoules per kilogram. Now, if I compare these two values, which one's greater, S2 or S1? S2 is greater. Does that make sense that it's greater? Sure. Let's do our entropy balance. Entropy balance, our second law, what does it say? Well, I know that I'm running out of room, so I'm just going to read it out loud. I have some incoming entropy with the mass. And then I'll have some entropy generation per mass flow rate through it. And all of that has to be swept out, taken out. And there's no way it can go out with heat transfer. It has to go out with the outgoing mass transfer. So S2 takes it away. S2 is greater than S1. By how much? By the amount of irreversibilities that generated the entropy. So if I'm looking for, I'll come up here now, sigma dot, is that equal to the mass flow rate times S2 minus S1. Good, on algebra. They gave me mass flow rate, and we calculated the S's, and so here's the rate of entropy production. The rate of entropy production, I never calculated. I did it the other way. Sorry. You can calculate it. I did it with the exergy balance. .13605. Okay, and now the units on that, kilowatts per Kelvin. Make sure you work your units carefully and slowly. I have the advantage, I've taken this class before, which means that I go a little too fast on units, but I can't go as slow as some of you need to go. You know what I mean? You need to go slow on your units and make sure you get them down. Does that look like the right units, kilowatts per Kelvin? rate of entropy generation. Then you multiply by 298 Kelvin, and what do you get? 298 Kelvin. 40.5 kilowatts. Check out the units. They all work, and that's the correct answer, 40.5 kilowatts. That's the rate at which the potential to do useful work is being destroyed due to the irreversibilities in this valve. Okay, now for part B. The annual cost of the exergy destruction, you want to calculate that, assuming 8,400 hours of operation per year, and the value of the exergy is 2 cents per kilowatt hour. This is kind of a funny unit, but it's common out there, kilowatt hour. I should have maybe put an asterisk or a dot between the W and the H. It's a multiple of kilowatt times an hour. You buy electricity in that unit. All right, so 2 cents per kilowatt hour. So we want to calculate what does it cost per year, something like that, okay? So it's the annual cost. Well, what I have to do is I have to get how much is destroyed per year. How much is destroyed per year, okay? Then I multiply it by the cost of the exergy that's being destroyed, okay? So how much is being destroyed per year? Well, it's going at 40.5 kilowatts, and that's going for a total of how many hours? 8,400 hours per year that steam is flowing through that valve. It's like it's running all the time, okay? So now you can see this funny unit of kilowatt times hour show up. So that's how many kilowatt hours is a unit of energy, kilowatt hour, per year that have been destroyed in that valve. Now multiplied by the value or the cost of that, and it's $0.02. That's 2 cents, right? 2 pennies per kilowatt hour. Let's go ahead and get rid of the kilowatts, get rid of the hour, and then we'll have so many dollars per year, right? So we'll get the cost, $6,810 per year. That may be below your radar for the company, to go in and try to optimize the system by eliminating that. Or it may be where you need to focus on that. Maybe $6,000 a year is a big deal to your company. We don't know. I suspect it's probably not. It's a little bit of money. Often you can find things to do in a plant to improve the efficiency that have great returns on your investment of time and resources. But this is just trying to quantify how much is lost. What's that cost? Ready for another problem? Yes. So a water pump intakes 6 kilograms per second of saturated liquid water at 10 kPa and discharges the water at 10,000 kPa. So we draw our image of a water pump. Comes in at state 1, exits at state 2. There's power being supplied to that water pump. The pressure at 1 is known to be 10 kPa. It's also known to be saturated liquid. Okay. At state 2, it's going out much higher pressure, 10,000 kPa. Right? Okay. They also give me the isentropic efficiency of that pump. Let's put it over here. The isentropic efficiency is 80%. Determine the power required to drive the pump for part A. What are we asked to solve for? What symbol am I going to use, and what are the units of that entity that I'm going to calculate the answer for part A? Am I going to calculate W dot pump? Is that right here? And how about units of kilowatts? Yes. Look reasonable? All right, very good. How do I want to do this?
You have the isentropic efficiency, so you just manipulate
Right.
to solve the
So the isentropic efficiency of the pump is a ratio of 2 works per unit mass. One is smaller, put that in the numerator. One is larger, put that in the denominator. The work isentropic compared to the work actual. The work per unit mass isentropic compared to the work per unit mass actual. Okay? So if the pump was isentropic, so it was no irreversibilities in the pump, isentropic flow through the pump, versus the actual pump, which has some friction in it. Okay, which one is going to be greater? Did I tell you already to put away the clickers? No problem. Keep them away. So we'll just take a volunteer to tell us out loud.
isentropic work would be smaller since there's less work required.
That's right, because it's a work required going into the system. The pump has to be supplied, so that's less. So it's going to be a funny one. Actual is isotropic over to actual. Okay. So if I was able to get lowercase w actual, I would multiply it by m dot, and that would give me what I'm looking for, w dot into the pump. True? Well, how do I get lowercase w actual? That's equal to the 1 over the efficiency of the pump times isentropic work of the pump. Okay? How am I going to get the minimum work required to drive that pump? To achieve the goal of the pump is to boost the pressure from 10 to 10,000 kPa. How do I get that minimum work per unit mass? It's going to be reversible. That's exactly right. And there's a little shortcut. It's at the end of Thermo 1. It's in Chapter 6. It's at the last section of Chapter 6 in our textbook. It talks about the exact problem we have. And you get an equation that is something like the work, internally reversible, int rev, equal to negative integral VdP. Warm, fuzzy feeling? Does it resonate? And so if you have, you're doing a pump, the specific volume of saturated liquid, and what's coming out of the pump? Compressed liquid. It's liquid, 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 liquid going through the pump, right? Is it going to be compressed, or is V constant? The specific volume is constant of liquids. That's our big assumption. It's well justified. So then that comes outside, and you just have minus V dP, so P2 minus P1. So if you have a pressure increase, the outlet pressure is higher than the inlet pressure, then that sign takes care of it because we know it's having to supply energy in the form of work to the pump. All right. So what we do is we say, okay, let me kind of go up here and do it. Or maybe I'll make some room up here. I'm trying to fit a lot in here. So we have the work isentropic is going to be the specific volume of the inlet pressure at state 1 times the pressure exit minus the pressure inlet. I dispense with the negative sign because, you know, I know it's not out. The pump is not work producing, it's work consuming. So let's do it that way. We go look up our specific volume, and it's typically very, very small. 0.00100102 meters cubed per kilogram. Look reasonable? Then we have 10,000 minus 10 times kilopascal. Now, what is a meter cubed times a kilopascal? How do those units convert? It's precisely a kilojoule. So we get that the work, the minimum work, if that was a perfect pump, would be something like 10.092. I know that's too many units, but we're continuing to keep as many units as we can in intermediate calculations. Kilojoules per kilogram. Make sense? So if you wanted to, you could find the specific work actual. That's 1 over the 80% for the isentropic efficiency times Ws, and we calculate it to be right at 12.6 kilojoules per kilogram. It takes more work because we have irreversibilities to achieve the same pressure increase for the pump. All right, so what we find is cap W dot P of the pump, that's this specific work times the mass flow rate of 6 kilograms per second, comes in at 75.7 kilowatts. And I hope I left myself enough room to answer part B now. What is the rate of exergy destruction in the pump? The rate of exergy destruction in the pump. Right, so we're looking to calculate for this answer E dot D, and it's in units of kilowatts, true? Okay. How would we calculate that? I know I could discuss this for a little bit, but the mass flow rate times the lowercase w sub a, we just calculated that. That's the power being supplied to the pump. 75.7 kilowatts are being supplied to the pump, right? Where does that 75.5 go? Some of it goes to increasing the flow energy or the flow exergy of our liquid water. How much goes there? Well, that's what we calculated before. It's the minimum work in to achieve that increase in pressure. And so you would calculate, just take the difference of these two, and you get that it's about 15.1 kilowatts. So some of that pump energy, the difference between 75 and 15.1 is right 60.6 kilowatts. That goes into increasing the fluid flow exergy. All right. Now the last part, part C, the exergetic efficiency. Well, what is my exergetic efficiency for this pump? Something like what I desired over what it costs. What do I desire? A large increase in the fluid flow exergy. What was the actual increase in the fluid flow exergy? 60.55 kilowatts when you carry more digits. And what did it come at? It came at the expense of the pump power supplied to it, 75.7, or if you carry more digits, 69 kilowatts. And so you find that the exergetic pump efficiency is 79.99%. Hey, 79.99% sure does look like another number that I've seen in this problem. It's the same. Here's a case where the exergetic efficiency is the same as the isentropic efficiency. All right? The isentropic efficiency is the same as the exergetic efficiency. Did that all make sense? All right, I'm glad I didn't run out of time. I don't think I have enough time to start another problem. So thank you very much for your attention.